Stray reflections are not too annoying. This is now continuing on with test 2, the computational problems. This is problem 2. Let's see what it is. An infinite plane holds a charge of 10 to the minus 15th coulombs per meter squared. Figure out the electric field for the plane. That is, even if you remember it, show how you determine the electric field. A proton 1 meter away has a velocity of 100 meters per second in the direction of the plane. Where does it come to a stop? Okay, so let's go ahead and draw the picture for this to begin with. So we'll go ahead and here's our infinite plane, quote unquote. I'm drawing edges on it, but that's just because I can't draw out to infinity. It would take too long. So let's go ahead and put this on the x-axis here. We can put this on y and z. And we've got a proton right here that has some, or I'm just going to, for the moment, I'm just going to call it a charge. And it has a mass, and it has some velocity v0. And it's going to, the expectation is, it's going to come to some spot. I'll go ahead and call this x1. The expectation is going to come to spot x1, and it's going to stop. And we're going to determine if that's true, and if it is true, we're going to determine what is x1. That's our job. Okay, so first thing we're asked to do is, we know this is sigma here. Okay, so we know we have a charge sigma, which means we know we have a field that's associated with this as well. So what is this problem about? Well, this problem is, this is a positive charge, this is a positive charge. They are going to repel one another. However, this has some initial kinetic energy that's moving in this direction, some initial velocity. It's moving in this direction with a certain amount of kinetic energy. And it's going to move here until it runs out of that kinetic energy. Well, what does that mean? It means it's moving from a region of low potential energy into a region of high potential energy. Because you know, kinetic plus potential energy is always constant. So if the kinetic energy is decreasing, the potential energy is increasing. Okay, so this now becomes a problem that it's a conservation and energy problem, and as soon as we look at it that way, doesn't have to be that way, by the way, there are other ways to solve this, but as soon as we look at it that way, we realize all we need to do is know the difference in electric potential between this point here, which I'll call x0, and this point here, x1. We need to know the difference in potential energy between those two spots, and we'll be done. That's all there is to it. Okay, so what do we need to do in order to do that? Well, we need to know the electric field associated with this. And once again, I'm just going to do this. When I said show what this electric field is, this is how simple it is, right? I'm going to make some Gaussian surface, and even though it's not really clear from how I'm drawing this Gaussian surface, the infinite plane bisects that Gaussian surface, so it's equally on both sides. It's some area A. And by symmetry, I know that this field is normal to this surface, which means I do not need to worry about any one of these 6 surfaces on the plane. I just need to worry about the 2 end faces. I also know by symmetry that the value of the electric field at anywhere along that plane is going to be the same. So this is a perfect setup for Gauss's law. So what is this? My area here is just A. My electric field is just whatever E0 it is, and so that is E dot dA around that closed surface is AE0 on this side, and then on the opposite side here I get the same AE0, so I have 2 AE0, and what does that equal? It equals the enclosed charge divided by epsilon 0. And what is the enclosed charge? Well, it's just sigma, the charge density, the area charge density, times the area, which is A. So that is just sigma A over epsilon 0. And when we do the algebra, we see E equals, there's no minus sign, sigma over 2 epsilon 0. Okay, so there we are. Now, we also know that this equals the gradient of some potential. And because it's a uniform electric field, we know we don't need to worry about actually doing the differential or integral formulation of this. We can just look at macroscopic quantities, delta V, delta X. And we know that minus delta V equals E0 delta X. Okay, so what is the potential at this point right here? Well, let's look at it this way. So the potential at, let's look at the difference between the potential here and the potential at infinity. So what I'm going to do when I do that, I'm going to cross out this delta, because as soon as I'm doing comparing it to a zero reference, then I don't need delta anymore because the delta is from zero. Okay, so this is what we know. We know, I'm sorry, in E0 we know the value of E0 too. It's right here. Okay, so our potential at x0, V of x0, is going to be the difference between V of infinity minus V of x0. All right. And now, what is our expression? It's just this expression right here with this sigma over 2 epsilon 0 plugged in. So we just have sigma over 2 epsilon 0 and x infinity minus x 0. Can you tell I'm doing this at the end of the day? Okay, but what do we say about the potential at infinity? What we do is we say we're just going to set that potential to be equal to 0. We're defining the 0 point to be where the potential would be sigma x infinity over 2 epsilon 0. So this term just goes to 0. So we now can say V of x0, I'll write it here, V of x0 is simply equal to minus sigma x0 over 2 epsilon 0. Okay, now what's the expression for x1? What is the potential at x1? Well, it's just the exact same thing, right? I'm just replacing x0 with x1. I'm going to do this exact same integral here, and so I'll end up with minus sigma x1 over 2 epsilon 0. Okay. Oh, shoot. That might not be showing up on your screen. I want to make sure it shows up. So this is what we now have for our two potentials. Our potential at x0 and our potential at x1. All right. So now we are pretty much done, because what is our potential energy? Potential energy, you will recall, the electric potential is just the potential energy divided by the charge. Guys, the trouble of looking at me struggle to find where all these quantities were written down. And so where we were just talking about how potential energy is just charge times the electric potential. And we know that energy is conserved. Our initial kinetic energy, and I can't remember if I said this in another video, but they commonly will write that as T. So T plus U, our T1 and U1 is going to equal T2 plus U2. Okay, so actually I'm going to change this. I'm going to call this 0 since I called everything else up there 0. So we're going to say this is the difference between 0 and 1 instead of points 1 and 2. So what is our initial kinetic energy? That's just 1/2 mv0 squared. What's our initial potential energy? That is minus sigma x0 over 2 epsilon 0. But there's a Q times this because that's the potential, so we need Q times that to get the potential energy. And what's our final kinetic energy? We're hoping it's 0. And so we're going to assume it's 0 because that's what we're trying to find. Where is the location where the kinetic energy is 0? Then we have our U1, which is minus q sigma x1 over 2 epsilon 0. Okay, and what are we trying to solve for? We're trying to solve for x1. So I'm going to go ahead and I'm going to do some divisions here. I'm going to divide everything by this. So we have 2 epsilon 0 over 2 m v 0 squared, 2 epsilon 0, over q sigma. And we've got, do I have everything there? Yeah. Epsilon 0, q sigma, mv0 squared. Excellent. And here I just have a, everything divides out except for my x0, because this q sigma 2 epsilon 0, q sigma 2 epsilon 0 just divides out. Oh, no, let's go ahead and do that. We can do that. Although, yeah, how do I have a minus sign wrong here? I don't know. We'll find out. Anyway, this is x0 equals minus x1. Why do I still have that minus sign? I don't know. I'm not going to worry about it right at the moment, but a minus sign might be wrong there. Okay, so let's see. So epsilon 0 m v0 squared over q sigma minus x0 equals minus x1. Do we know x0? Yes. Do we know epsilon 0? Yes. Do you know m v0 squared q sigma? Yes. So we are done, with the exception of messing up a minus sign somewhere, which I'm fairly certain I did. Okay. So there we are. So all we're going to do is multiply these things out, and we're going to hope that I didn't screw things up too badly when I set this up, but I may have. So let's see what happens. 9 times 10, well, 9, this is our epsilon 0, 9, what's our m? 1.7. So you have a 9 times 1.7 here, times 10 to the minus 27th, and 10 to the minus 12th, that's 10 to the minus 39th. Okay, and this is over q times sigma. Q is 1.6. Sigma is just 1 times 10 to the minus 15th. So it's 1.6 times 10 to the minus 15th and 10 to the minus 19th, which is 10 to the minus 34. And meanwhile, I have a 100 up here for my V0. I have 100 squared. By the way, in case you don't know, I'm just doing this term right here, right now. Okay, 100 squared. Well, 1.7 over 1.6, that's pretty much 1. So we have 9 times 10 to the, I'm going to lift this up just a little just so you can see that, and then I'm going to move it upwards. So we have, this is 9 times 10 to the minus 5 times 10 to the 4th from my V0 squared, which is just equal to 9 times 10 to the minus 1, or 0.9. Now, we're going to put that into here. Yeah, definitely have a minus sign somewhere wrong, but I'm not going to worry about it. Like I said, everything will be minus. So we have a minus 1 is where we started at. I mean, we started at 1. Man, sorry, I don't know what I screwed up there, but I'm not going to worry about it, because what I'm going to do... Okay. Yes, what I'm going to do is I'm going to say, all right, this was 0.9. Our initial was, our initial x1 was 1 meter. And so our difference is 0.1 meters. It's minus, I think I know where I screwed up, but I'm not really worried about it. Because what I do know is it stopped in 0.9 meters. started 1 meter away. Therefore, it is 1/10 of a meter away from here. And I believe that's what we're asked to find. So where does it come to a stop? Yep. So it comes to a stop at 1/10 of at x1 or x1 equals 1/10 of a meter. And you're done. And you'll notice every step of that were things that you guys have done. Gauss's law for a uniform charge plane, no problem for you guys. Potential difference, no problem for you guys. Q times potential difference is potential energy, no problem for you guys. And then just conservation of energy, that's it. So it takes a lot longer to talk about than it does to actually do it. So that's it.